Hi, my name is Tim Rukop and I'm presenting to you our recently accepted TMLR publication called MASIF, an implicit multi-fidelity algorithm selection method. That is joint work by Aditya Mohan, Tifan Deng, Alexander Tornede, Frank Hutter and Marius Lindauer. First off, let's set the scene and gain some intuition of what a data scientist's workflow looks like. As a data scientist, we have experience with the algorithm of our domain and how they have performed on past datasets. Selecting the best algorithm for a new dataset is crucial for developing successful AI and ML applications, but it can be time-consuming and tedious. Based on our probably extensive EDA and all of the observed learning curves of our algorithms, we as well may have some intuition about the subtleties of our datasets. When faced with a new dataset, we can leverage all this experience and to make fast and elaborated guesses on which algorithm likely performs best. Data scientists may formulate a hypothesis on which algorithm may work best and check it out. Given the new evidence they gather, they may update their hypothesis and probe again and again, each time learning something more about the dataset's subtleties and which algorithm may work best. We can also iteratively allocate more budget to our algorithms, until we are confident enough about which algorithm we want to choose. Crucially, we may not need to evaluate all of the algorithms fully, or even exclude some of the algorithms entirely from our evaluation process. So what in essence we strive for is an iterative discovery process that is fully flexible in the budget allocation and can leverage prior experience with algorithms' learning behaviors. We want to use this prior experience to interpret partial learning curves jointly with respect to the selection problem on a new dataset. Let's back up a little and check out what the literature has to offer. Classical algorithm selection usually considers dataset meta features, which I called EDA earlier, and tries to cross-correlate them with the validation performance on a dataset after fully training all algorithms until convergence. When facing a new dataset, without being eligible to look at the algorithm's performances and forced to solely rely on the similarity in the meta feature space, we need to make a prediction on the ranking of the algorithms for a new dataset. The quality of our selection is ultimately dependent on how well the meta features are indicative of the performance. This requires considerable engineering effort in developing the right meta features and offers no guarantees for a new dataset. And we have left a lot of intermediate performance data that is usually tracked anyways on the table, which leads us to an alternative approach, namely multi-fidelity. In essence, it seeks to utilize low-cost approximations to cheaply determine the final outcome. For our problem proposition, let us simplistically exploit learning curves like a data scientist might. For instance, we could take a single partial learning curve from an algorithm, make some parametric assumption, and fit our best guess curve to extrapolate it to the final performance. If we did this for all the algorithms respectively, we can formulate our expectation of which works best. But we have used a lot of simplifying heuristics. First, we had to make parametric assumptions. Second, we had to base our extrapolation solely on what we were able to observe. We refer to this as myopia or short-sightedness. Third, we have to evaluate all of the algorithms to get some idea about their likely trajectory. And lastly, we have ignored anything we might have known about the past datasets or how one curve might be elucidating for another. Enter our MASIF architecture. Let's start at the top with where we want to end up before we figure out how we get there. We want to formulate a ranking over all our candidate algorithms. To do so, we utilize torch sort with Spearman ranking as a differentiable ranking loss. Let's go to the bottom of it. For now, let's assume we only had learning curves and ignore both the dataset meta features and algorithm meta features, which are optionally here anyways. We also introduce an end-of-sequence token, which we abuse to avoid technical issues in the attention mask later on, and allow us to explicate our model's expectation when zero fidelity information is available. We then project the padded learning sequences and add to it a positional encoding based on the amount of fidelity. Consider that each learning curve corresponds to a sentence in a language task. We feed the set of candidates as a batch of independent sentences that are causally masked by our data augmentation scheme through the first transformer layers. As data augmentation strategy, to avoid overfitting on small datasets and to allow our model to interpret any budget allocation, we use uniform max budget masking on the learning curves individually. That is, for each curve in the batch, we uniformly sample some maximum fidelity after which the curve is masked. The output of this encoder is a marginal summary in form of a vector for each learning curve individually, stripped of its sequential nature. To interpret the learning curves jointly, we transpose this batch and feed it through the next transformer across the vector dimensions, without any masking to learn how they cross-correlate. Afterwards, we transpose the batch again and project it yet again to the number of algorithms before evaluating with our ranking loss. Two things I briefly want to elaborate on are the motivation for the classical dataset meta features, which may be slightly informative, and the algorithm meta features. First off, if the dataset meta features are indeed informative, we may want to influence what we attend to. Second, algorithm meta features may be available in form of hyperparameters and alter the learning behavior. We utilize this, if available, akin to a positional embedding to contextualize how the summarized learning curve vectors relate to each other. But how does this look like in practice? Let us set some ground rules for evaluation. I introduce to you the slice evaluation protocol. We start with the classical setting of 0% available fidelity to our selector, relying purely on classical dataset meta features. Then we iteratively keep on expanding the fidelity horizon, meaning we allow the selector to see all of the partial learning curves of all algorithms up to the fixed amount of fidelity, for example, 20%. We measure using top K regret, that is, how much test performance we lose for a new dataset if we choose the predicted best K algorithms and train them fully against the actually best algorithm. What we want to check for is the influence of meta-knowledge when there is no fidelity information available, how fast the algorithms adapt to incoming fidelity information, and at last, what the final incurred regret is. Here, we have a dataset called task set that is consisting of the learning curves of many optimizer configurations applied to neural network architectures on images. In task set, we lack both the dataset meta features and algorithm meta features, such that we can solely rely on the past experience from the learning curve trajectories. Aggravating, the learning curves are very noisy, which reflects in the worse than random guessing performance of successive halving and remaining regret because of the noisy target. At around 10 to 20% of additional fidelity, we can disambiguate the incoming curve information considerably. This is way faster than without prior knowledge, as we can see in the red curve representing our naive learning curve extrapolation strategy from earlier. At this point, I would like to highlight MASIF's capability to interpret any set of partial learning curves in the context of its meta experience. While the slice evaluation protocol expands the fidelity horizon of all algorithms equally, successive halving did not benefit from it, due to its rigid schedule, which leads to path dependencies and inferior performance, at notably lower cost. For illustrative purposes, we inserted MASIF as add-on to successive halving that decides at every of successive halving's brackets which algorithms are currently the best contenders and should be continued. It decides based on the entire allocated budget and the resulting observed partial learning curves. As a consequence of successive halving schedule, this combination requires considerably less budget. But MASIF's meta experience drives the regret behavior. Eventually, this simple combination suffers from successive halving's path dependency and cannot recover from bad selection decisions later on, leading to a slight inferior performance. But it does so at considerably lower cost. There is a lot more to unpack, so please check out our paper for more results. But in summary, MASIF can help guide rapid prototyping, leverage invested computation from past experiments, interpret any budget allocation on a new dataset, and help build schedules for iterative budget allocation, and how to build the optimal schedule given past experience and incoming evidence. That's it, folks. Thank you for your interest, and please check out our paper at TMLR.